Hello, and welcome to Quiet Learning for Sleep. This is your peaceful space to unwind, to let go of the day, and to drift into deep, restful sleep while learning softly about our universe. Here, we take gentle journeys through calm ideas, stories from science and nature, space and time, history and life, all whispered at a soft pace, without rush, without noise, and without pressure. You do not need to focus or remember anything. This is learning the quiet way, where your mind floats and drifts and rests, while curiosity stays softly awake in the background. If you'd like, before you get comfortable, you can subscribe and gently like this video. Doing it now means you won't forget later, and it helps others like you find this calm, sleepy corner of the world. Now, allow your breath to slow just a little. Let your shoulders relax. Let your thoughts soften, like clouds drifting across a calm evening sky. There is nowhere you need to go, nothing you need to do, and nothing expected from you here. This time belongs to rest, comfort, and gentle curiosity. And if you drift to sleep along the way, that is not only allowed, it is welcome. So settle in, let yourself melt into stillness, and allow your mind to float quietly as we begin. In the vast darkness of space, where silence stretches beyond imagination, clouds of gas drift for millions of years. Invisible to the eye, they gather slowly, atoms of hydrogen and dust left behind by ancient stars. These clouds are cold and dark, hundreds of light years across, floating like cosmic mist between the stars we see at night. Yet within them lies the potential for new light, for the beginning of everything we call a star. The process begins almost imperceptibly. A small region inside a molecular cloud grows denser than the rest, perhaps nudged by a passing supernova shockwave or the gravity of a nearby cluster. Over time, that density pulls in more material, and gravity begins to do what it does best. It gathers. As the cloud collapses inward, its center grows warmer. At first, this warmth is only a whisper, but it marks the start of transformation. In that moment, a star is conceived, though still hidden within its cocoon of dust. The Orion Nebula, known as M42, is one of the most breathtaking examples of this process. Visible even to the naked eye beneath Orion's belt, it glows faintly as a smudge of light in the night sky. Through a telescope, it reveals a luminous cloud of pink and violet gas, illuminated by the young stars forming inside it. There, more than 1,000 newborn suns ignite in the same region, a stellar nursery, just 1,300 light years away. Each of those glowing points is a new beginning, some destined to live for trillions of years, others for only a few million. As gravity compresses the collapsing core, pressure builds until the atoms of hydrogen begin to fuse. This is the miracle of nuclear ignition, the moment when a protostar becomes a true star. Temperatures soar to more than 10 million degrees, and light begins to flow from the center outward. For the first time, the object pushes back against gravity with its own energy. The long balance between collapse and pressure begins, defining the rest of the star's life. If we could stand near such a young star, we would not see its light directly. Its birthplace is thick with dust, glowing faintly in infrared, invisible to human eyes, but radiant to space telescopes. The Hubble and James Webb observatories have peered into these cradles, Orion, Taurus, Carina, and revealed thousands of tiny points of warmth, each wrapped in swirling disks of gas and dust. Those disks will one day form planets, moons, and rings. a solar system is being written into existence. In the Taurus molecular cloud, only about 450 light-years away, astronomers have watched dozens of protostars emerge. Many of them are small, less than half the mass of our Sun. Others, still gathering material, may grow to several times heavier before their collapse ends. Compared to our Sun, whose mass defines the standard, these forming stars are unpredictable. Some will end as gentle red dwarfs. Others will flare into short-lived blue giants that burn out in cosmic instants. Mass decides everything in a star's destiny. Our own Sun began this way about 4.5 billion years ago. It was once part of a cluster of hundreds of stars born from the same cloud. We can still trace its likely birthplace in the constellation Hercules, where faint remnants of that original nebula drift. Like its siblings, the Sun formed when enough mass accumulated to ignite fusion. At one solar mass, it achieved perfect balance, neither collapsing nor exploding. Most stars, however, are smaller, burning dimly and far longer. For every sun-sized star, there are hundreds of red dwarfs with half, or a tenth of its mass, glowing faintly for trillions of years. Inside the Orion Nebula, we can see examples of every stage of stellar birth. There are cold knots of dust still collapsing, glowing spheres already ignited, and clusters of young stars that have just cleared their surroundings. The trapezium cluster, near the nebula's heart, contains 4 brilliant blue-white stars, each about 20 times the mass of the Sun. Their fierce radiation carves away the gas around them, shaping the nebula into wings of fire. Yet, for all their beauty, those stars will live short lives, just a few million years, before collapsing into supernovae. Mass gives brilliance, but steals time. The newborn stars emit strong, stellar winds, streams of charged particles that blow outward, sweeping away the remaining dust. When that dust clears, the stars emerge fully visible. The nebula fades, its work complete, leaving behind clusters of young suns shining together. We can still see such clusters across the night sky. The Pleiades in Taurus, the Hyades near Aldebaran, or the open clusters of Auriga. Each is the remnant of a nebula that once glowed and nurtured new light. Even now, the cycle continues everywhere we look. In the Eagle Nebula, 7,000 light-years away, towers of gas rise like fingers into space, the famous pillars of creation. At their tips, new stars are being born at this very moment. Some of them may one day shine bright enough to be seen from Earth, while others will live their entire lives hidden in dust. The process is the same across galaxies. Gas collapses, fusion begins, light awakens, and the darkness becomes a little less absolute. When we gaze up on a clear night, many of the faintest stars we see are young, only a few million years old. Others are ancient veterans, billions of years in age, but every one of them began in the same way, as a small gathering of atoms collapsing in the cold. Their light is the record of that beginning. Even the familiar stars of Orion, the red giant Betelgeuse, and the blue-white Rigel, were once no different from the protostars glowing now in the nebula below them. The heavens are both archive and nursery, showing birth and legacy in a single glance. To imagine a star being born is to witness balance itself taking shape. Gravity pulls inward, fusion pushes outward. The result is stability, an equilibrium so perfect that it can last billions of years. From this point onward, the young star joins the main sequence, shining quietly and steadily until its fuel begins to fade. It will have planets, moons, perhaps even life. But for now, it simply glows in silence, a newborn sun among thousands. Somewhere, in some nebula, another light is just now beginning to shine. Though every star's birth follows the same laws of physics, no two regions of creation look alike. In the Carina Nebula, 7,500 light-years away, massive columns of gas rise like mountains adrift in space, each taller than our entire solar system. Within those pillars, clusters of embryonic stars flicker faintly, hidden behind curtains of dust. Infrared telescopes can see through the haze, revealing the first sparks of fusion beginning deep inside. The scene resembles a silent thunderstorm, light without sound, energy without chaos. Closer to home, in the Rho Ophiuchi cloud complex near the border of Scorpius and Ophiuchus, smaller stars are forming right now. The cloud glows softly in reds and purples, illuminated by ultraviolet light from nearby giants. Some of its newborn suns are visible through amateur telescopes as faint orange dots, only a few 100,000 years old. Compared with the sun, they are mere infants, just 1,000th its age. Yet even at this stage, they already possess the mass and temperature that will define their entire lives. Each stellar nursery is a balance between light and shadow. The very stars that are born within it eventually destroy it. Their ultraviolet radiation pushes the gas away, sculpting bubbles and waves that reveal more and more of the cluster beneath. In this way, destruction creates beauty. The nebula glows most vividly when it begins to vanish. Over millions of years, the remaining dust disperses into interstellar space, leaving behind open clusters like the Pleiades, groups of young blue stars shining against the dark. The life of a nebula ends in brightness, not in silence. Sometimes, the opposite happens. A massive star nearby reaches the end of its life and explodes as a supernova. The shockwave races outward, compressing nearby gas clouds and triggering new waves of star formation. The death of one generation becomes the birth of another. The atoms forged in that dying star, carbon, oxygen, iron, mix into the next, ensuring that every new sun carries traces of what came before. In this way, even stars are part of a lineage. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were born in the heart of stars that lived and died long before the sun existed. In the Perseus molecular cloud, a vast and cold region stretching hundreds of light years, astronomers have recorded the same story playing out again. Small knots of gas are collapsing, each forming a protostar hidden in infrared glow. When mapped, these knots resemble constellations, miniature galaxies within a single cloud. Some will never ignite. They will remain as brown dwarfs, too small to begin fusion, cooling slowly for eternity. Others will grow to many times the sun's mass, blazing blue and fierce for only a few million years. Every cloud writes its own statistics, but the melody is the same. Gravity gathers, fusion begins, light endures. If we could speed up time and watch from afar, the process would look like a slow-motion dance. Dark clouds would twist and fold, bright spots would appear, and the surrounding gas would glow as the newborn stars began to shine. What now takes millions of years would unfold like the blooming of flowers, each one radiating warmth into the void. The sky would shimmer with new constellations, their light spreading across the galaxy. And somewhere, perhaps on a distant world yet unformed, life might one day look back and wonder how it all began. Even after a star is born, the cloud that created it continues to shape the universe. The leftover gas becomes the raw material for planets, comets, and asteroids. The heavier elements, carbon, silicon, oxygen, bind together to form dust grains, which cling and merge inside the circumstellar disk. Over time, these grains become pebbles, then rocks, then worlds. Every planet is the echo of a star's creation, molded from the fragments left behind. When we walk upon Earth's ground, we are literally walking on the remains of a nebula that once glowed with the same quiet light as Orion. And so, in every corner of the galaxy, the same story repeats. Clouds collapse, stars ignite, nebulae fade. It is an unending rhythm, birth, brilliance, and dispersal, woven into the very structure of the cosmos. To watch a star being born is to glimpse the essence of creation itself, the universe learning to shine again. The light that reaches our eyes on a clear night carries those beginnings across space and time. Each photon is a message, traveling for centuries or millennia to remind us that even the darkest regions hold the seeds of dawn. The next time you look up and see the faint smudge of the Orion Nebula, know that you are seeing life in its first breath, a cradle of energy, color, and silence. Every spark within it is another sun waiting to rise, another future world waiting to orbit that light. From the smallest red dwarf to the brightest blue giant, every star begins in the same fragile balance, the same gathering of dust and gravity. And just as surely, every one of them will someday fade, leaving behind the material for another generation to begin anew. The universe does not tire of creation. It merely pauses to breathe. Before a star truly awakens, there is a long and quiet phase, a stage of waiting, of almost light. Within the vast clouds of hydrogen and dust that float between stars, pockets begin to stir. They spin, twist, and collapse inward, forming what astronomers call protostars. These are suns in rehearsal, not yet ready to shine. The airless darkness around them grows heavy with motion, as if the cosmos itself were inhaling before speaking its first word. A protostar is both fragile and fierce. Gravity pulls the gas inward, while trapped radiation pushes outward. The temperature rises, but not enough to ignite nuclear fusion. Instead, the growing heat glows softly in infrared, light that our eyes cannot see, but our telescopes can sense. Through instruments like the James Webb Space Telescope, astronomers peer into these hidden nurseries and watch the faint amber warmth of a forming sun, still wrapped in its birth shroud. In the Eagle Nebula's towering pillars of creation, dozens of such protostars nestle inside the columns of gas. Each one is a small seed of gravity, less than 1 million years old, surrounded by whirling disks of dust. The material spirals inward like a slow whirlpool, feeding the young object at its center. Jets of energy burst outward from its poles, carving long, narrow tunnels through the surrounding cloud. These glowing beams, visible even in visible light, are the signatures of a star being born. Protostars are often hidden from the optical sky, but their influence can be felt. In the Trifid Nebula, 5,200 light-years away, ultraviolet light from nearby newborn stars illuminates the gas, tinting it rose and blue. In its darker lanes, new stars are still forming. The balance is delicate. One star's creation can trigger another's birth, or halt it entirely. In this way, the cosmos writes its story in feedback loops. A single bright spark can change the fate of thousands yet unborn. Every protostar is wrapped in a disk, a wide, flat ring of gas and dust stretching billions of kilometers across. Inside this disk, collisions happen constantly. Tiny grains of ice and rock strike and stick, building up into clumps. The disk glows faintly, warmed by the young star's heat. As the protostar grows, it begins to clear the inner region, shaping a cavity that will later host planets. The same process that creates stars also creates worlds. The boundary between the two is simply a matter of scale. If we could stand near one of these embryonic suns, say, in the Rho Ophiuchi cloud, it would appear not as a point of light, but as a diffuse glow behind drifting curtains of dust. We would see ribbons of gas twisting in slow motion, glowing faintly from infrared warmth. Magnetic fields would thread through the cloud, invisible lines guiding the flow of charged particles. The silence would be total, broken only by the faint vibration of radiation, the soft hum of a star, not yet ready to sing. Protostars can vary enormously in size and mass. Some are barely 1/10 the mass of our sun, destined to remain dim red dwarfs. Others will gather 100 times more matter, growing into bright blue giants. The difference is decided early, often within the first million years. Once a protostar crosses the threshold, where its core temperature exceeds 10 million Kelvin, hydrogen fusion ignites. The protostar becomes a true star, and the nebula around it begins to fade. But before that ignition, an extraordinary phase occurs. Astronomers call it the T Tauri stage, named after a young star in Taurus. T Tauri stars are turbulent, variable, and restless. Their brightness flickers as they accrete gas, and they send out violent winds that push back the disk around them. Our own sun passed through such a stage billions of years ago, casting off waves of plasma that helped shape the planets. Even in infancy, stars sculpt their surroundings with both creation and destruction. In the Orion molecular cloud, hundreds of T Tauri stars shine softly in visible light. Many can be seen through small telescopes as a faint sprinkling around the bright core of the Orion Nebula. Each one glows with a warm, yellow hue, less intense than the adult stars nearby, yet radiant in its potential. Compared to the Sun, they are perhaps half as massive, their light far dimmer. But in their variability, we glimpse our own sun's childhood, a turbulent, luminous youth that ended in calm maturity. Stellar nurseries such as these are enormous, spanning dozens of light years. Inside them, hundreds of protostars coexist in different stages of formation. Some are still invisible knots within the darkest regions. Others have already broken free, shining blue and white against the remaining haze. It is a scene of contrasts, birth and decay, darkness and illumination, repeating endlessly across the galaxy. The same cosmic rhythms that forged our sun are playing out now, thousands of times over, in quiet corners of the Milky Way. When we observe these nurseries, we are not looking into space alone, but into time. Light from the Orion Nebula takes 1,300 years to reach us. From the Carina Nebula, 7,500. What we see tonight is ancient history still unfolding, frozen in transit across the void. Somewhere within those glowing clouds, new stars are being born this very moment. though their light will not reach Earth until centuries from now. To watch a protostar is to glimpse the past and the future at once. Eventually, the winds of the young stars clear away the last of the gas, leaving only clusters of light where once a nebula drifted. The darkness returns to that region of space, but it is no longer empty. It now holds hundreds of suns, each with its own retinue of planets, moons, and dust. The nursery has become a constellation, and its story is complete. But beyond its fady edge, in another cold region, the process begins again. Gravity gathering, light waiting, time breathing. From Earth, we can see these birthplaces scattered across the night. The Orion Nebula below Orion's belt, the Trifid in Sagittarius, the Lagoon Nebula glowing faintly near it. To the naked eye, they are pale clouds, but through a telescope, they reveal form and color, a reminder that the universe is not static, but alive. Each patch of light is a promise that somewhere, right now, new stars are stirring in the dark. The cosmos never sleeps. It simply dreams in nebulae. The protostar stage is brief by cosmic standards, barely a blink in the universe's age. But it is the most transformative. It is the time when chaos becomes order, when gravity learns to sing, when the first breath of starlight is taken. And though we cannot hear it, the echo of that moment fills the galaxy. It resonates in the warmth of sunlight on our skin, in the sparkle of every star above. The story of the protostar is the story of awakening, a slow, radiant dawn written in hydrogen and hope. Every star, no matter its size or color, spends most of its life in a long and peaceful balance. This stage is called the main sequence, the quiet heart of a star's existence, where the struggle between gravity and energy reaches a perfect, enduring harmony. Here, deep in the core, hydrogen atoms fuse into helium under immense heat and pressure, releasing light that has no end until the star's fuel begins to fade. It is a delicate truce, a conversation between collapse and creation that can last for billions of years. Our sun is a main sequence star, neither too large nor too small, one solar mass, glowing in steady golden light for the past 4.5 billion years. It fuses roughly 600 million tons of hydrogen into helium every second, yet loses almost no mass from our perspective. The balance is so perfect that its brightness barely changes across millennia. To us, this constant glow feels eternal, but it is the product of forces so immense that eternity is simply a fleeting stability. For every calm moment, an endless storm of fusion burns beneath the surface. The light that escapes the sun's surface is ancient by the time it reaches us. Each photon spends tens of thousands of years bouncing within the solar interior before finally emerging into space. Only then does it cross the void in 8 minutes to touch Earth. The warmth we feel on our skin is therefore both immediate and impossibly old, a fragment of energy born from a hydrogen nucleus that once collided with another deep in the solar heart, when humans did not yet exist. Across the sky, other main sequence stars live their own versions of this balance. Sirius, the brightest star we see from Earth, is about twice the mass of the sun and 25 times as luminous. Because it burns its fuel faster, it will live for only 1 billion years, just a quarter of the sun's lifespan. Its white-blue glow is crisp and strong, its heat almost double our stars. Sirius is a reminder that brilliance often comes at the cost of time. In contrast, Proxima Centauri, the closest star to our solar system, is a small red dwarf, only 1/8 the mass of the Sun. Its light is so faint that it cannot be seen without a telescope, yet it will live for trillions of years. Red dwarfs burn slowly, fusing hydrogen with exquisite efficiency. Their surfaces are cool, their flares occasional, their lifetimes nearly infinite. When every bright star in the galaxy has long since died, red dwarfs like Proxima will still be glowing softly, witnesses to epochs beyond imagination. Between these extremes lies an entire spectrum of starlight: orange dwarfs, yellow suns, white giants, each defined by mass, color, and chemistry. Small stars live long, steady lives. Massive ones blaze fiercely and fade quickly. The unifying principle is fusion, the conversion of hydrogen into helium, where tiny amounts of mass vanish and reappear as energy, according to Einstein's famous equation, E = mc². Every sunrise, every ray of light on Earth is powered by that same quiet transformation of matter into radiance. Inside a main sequence star, the pressure and temperature at the core determine which fusion cycle dominates. In stars like our Sun, the process is the proton-proton chain. Hydrogen nuclei merge directly to form helium. In larger, hotter stars, another route takes over: the CNO cycle, named for carbon, nitrogen, and oxygen. These heavier elements act as catalysts, speeding fusion and enriching the star's chemistry. Over millions of years, the interior becomes a crucible of transformation, where traces of carbon and oxygen accumulate, ready to be scattered into future nebulae once the star dies. It is within these stars that the universe's first complex elements are made. The simplest atoms, hydrogen and helium, were born in the Big Bang. But carbon, nitrogen, oxygen, and neon arise here, in the furnaces of main sequence stars. Every breath of oxygen we take, every molecule in our cells, every carbon atom in a leaf or heart, was once fused in the core of a star like the Sun. When such a star sheds its outer layers or dies, these atoms are released into space, becoming part of new clouds, new planets, and new life. Fusion is not just physics, it is ancestry. If we look up at Vega, shining bright in the constellation Lyra, we see another example of this balance at a different scale. Vega is about twice the Sun's mass and 40 times as luminous. It rotates rapidly, flattening slightly at its poles, and emits a blue-white light. Its spectrum reveals hydrogen lines mixed with traces of heavier elements, evidence of the complex fusion cycles within. It is a young star, only 500 million years old, glowing with the intensity of youth. One day, it will expand into a red giant, enriching the interstellar medium with the elements it created. Every color in the night sky tells us something about a star's life and chemistry. Red stars are cool, around 3,000 degrees Celsius, glowing softly in long wavelengths. Yellow stars like our Sun burn near 6,000 degrees, balancing brightness with stability. Blue stars exceed 20,000 degrees, brilliant, powerful, and fleeting. These colors are not illusions, they are fingerprints, written in light by the elements within. Astronomers can read those fingerprints and determine a star's temperature, motion, and age simply by studying its spectrum. The universe speaks in color, and stars are its language. In the main sequence, time flows differently. Small stars tick slowly, their changes imperceptible across millions of years. Massive ones rush through their youth, exhausting their fuel and preparing for explosive futures. Yet in both cases, the outward appearance is one of serenity. To an observer, a main sequence star seems constant, unwavering, eternal. But beneath that calm exterior, a billion reactions happen every second, turning matter into light with silent precision. If you were to stand on a planet orbiting another sun, a stable orange dwarf or a distant white star, the light falling across your face would feel both familiar and strange. It would be the same warmth, the same fusion energy, the same ancient process repeating itself across the galaxy. The only difference would be the hue, the subtle tone of gold or blue, the flavor of the elements within. The laws that govern one star govern them all, linking every world and every life under the same universal rhythm. The Sun, Sirius, Vega, Proxima Centauri, Alpha Centauri, each a variation of the same song. Their masses differ, their lives unfold at different tempos, but they share the same origin and destiny. They are the steady heartbeats of the galaxy, maintaining its light through the ages. When we gaze at them, we see the middle chapter of cosmic existence, the time between creation and collapse, between birth and renewal. The main sequence is the universe's long exhale, a sigh of balance before the next transformation. Someday, every main sequence star will reach its end. Its core hydrogen will run low, fusion will falter, and gravity will once again begin to win. The star will swell into a giant, shedding its outer layers, or collapsing into something new. But for now, in this long era of balance, they shine with patience. The light that fills our skies tonight began its journey in those cores, and even after we are gone, it will continue to travel outward, lighting the darkness for ages to come. In every ray of starlight lies the memory of that harmony, a message from a universe that learned to breathe and to shine in peace. Among all the stars in the universe, most are not bright, nor blue, nor golden like our sun. The vast majority are small, dim, and red, stars so modest in their light that 1,000,000 of them together would not equal the glow of a single giant. These are red dwarfs, the quiet embers of the galaxy, the unending fires that will outlast every other kind of star. They burn low, but they burn forever. Red dwarfs make up nearly 3/4 of all the stars in the Milky Way. Yet from Earth, you can hardly see them. Their light is faint, their energy soft, and their color deep, glowing at temperatures between 2,000 and 4,000 degrees Celsius. While blue giants flare and fade in a few million years, red dwarfs can shine for trillions, longer than the universe has even existed so far. If eternity had a color, it would be the dull red of a dwarf star. The nearest star to our solar system, Proxima Centauri, is one of these quiet suns. Barely 1/8 the mass of our sun, it glows in crimson light, invisible to the naked eye. A telescope reveals it as a faint spark in the constellation Centaurus, orbiting alongside the larger stars, Alpha Centauri A and B. Though humble, Proxima is the closest neighbor to our sun, only 4.24 light-years away. Around it, at least one planet orbits in the habitable zone, where liquid water might exist. If life ever arose there, its skies would be dim and eternal, bathed in a twilight that never truly ends. Another nearby ember, Barnard's star, lies just 6 light-years away in the constellation Ophiuchus. It is twice as old as the Sun, and still burning steadily, its fusion rate so slow that it barely changes across billions of years. It moves swiftly across our sky, the fastest proper motion of any known star. Yet its journey is quiet, unseen by the unaided eye, a silent traveler glowing in red. What makes red dwarfs so enduring is their simplicity. They are fully convective, meaning that hot plasma from their cores circulates all the way to their surfaces and back again. This constant churning allows them to use nearly all their hydrogen fuel, while larger stars like the Sun burn only the material in their cores. Nothing is wasted. Their efficiency makes them nearly immortal, glowing at a whisper instead of a roar. Inside, the physics remains the same as in any star. Hydrogen nuclei fuse into helium, releasing light. But red dwarfs never reach the pressures or temperatures needed to fuse helium further. They will never create carbon, oxygen, or iron. Their chemistry is simple, almost minimalist, a slow alchemy that ends before complexity begins. Yet their simplicity grants them permanence. When all bright stars are gone, the red dwarfs will still linger, faintly illuminating the future darkness of the cosmos. Wolf 359, another nearby red dwarf, lies in Leo, just 8 light-years from Earth. It is one of the faintest stars ever catalogued, barely 1% as luminous as the Sun. From that world, if a planet orbited close enough for warmth, its daytime sky would still be dim enough to reveal the stars. There would be no harsh sunlight, no deep shadows, only a constant dusky glow. The rhythm of day and night would blur together into a quiet, timeless dusk. Because they burn so slowly, red dwarfs also evolve differently. They remain stable for tens or even hundreds of billions of years. When they finally exhaust their hydrogen, they will cool directly into blue-white embers called white dwarfs, skipping the red giant phase entirely. No cataclysm, no explosion, just a gradual fading into quiet light. These will be the last stars shining when all else has gone dark, their glow persisting in the far future, when the Milky Way itself has long since changed beyond recognition. Though dim, red dwarfs have a fierce side. Their magnetic fields can be volatile, producing sudden flares that bathe their nearby planets in radiation. Some of these outbursts are powerful enough to strip atmospheres away, rendering worlds sterile. Yet others may be mild enough to allow adaptation. If life evolves under such stars, it would be life accustomed to patience and endurance, a life built to survive in twilight and silence. Because they are so numerous, red dwarfs will one day dominate the night skies of far future civilizations. When all bright stars have faded, the universe will be filled only with their faint crimson light. Imagine a galaxy where the blue giants and yellow suns have long since died, leaving only a gentle scarlet glow spread across eternity. That will be the last age of starlight, a slow, soft whisper before the long cosmic sleep. In our own sky, even though you cannot see them unaided, red dwarfs surround us in every direction. The nearest few dozen stars to the Sun are mostly these dim embers. They form the unseen architecture of our galactic neighborhood. Every telescope image that peers deeply into the Milky Way captures countless red points of light, so faint that they merge into a diffuse glow. They are the quiet workers of the universe, maintaining its light without praise or recognition. If you could float near one, the scene would be serene and strange. The star would appear large in the sky, glowing with a deep orange-red hue. The the surrounding space would feel close, warm, and hushed. Light would move softly across your visor, less bright than a candle. In that gentle illumination, you would sense the enormity of time, a star that has burned for billions of years and will continue for trillions more. The silence would not feel empty, but eternal, as if you were standing at the heart of forever. Red dwarfs remind us that longevity does not require brilliance. They burn quietly, without spectacle. Yet they will outlast every giant and every sun. They are the slow pulse of the cosmos, the embers that keep the universe warm, long after the fireworks of youth have ended. When all other stars are gone, their glow will linger, soft and steady, whispering through the endless dark. I am still here. I am still shining. Between the eternal embers of red dwarfs and the fierce brilliance of blue giants lies a golden middle ground, a class of stars that shine with calm, steady light. These are the yellow suns, the balanced architects of life. They are neither too hot nor too cold, neither fleeting nor eternal. In their quiet stability, they provide the warmth and time needed for planets to grow, oceans to form, and life to awaken. Our own sun is one of them, a perfect example of how the universe can sustain harmony for billions of years. Yellow suns, technically called G-type main sequence stars, are rare compared with the countless red dwarfs that fill our galaxy. Only about 1 in 10,000 stars burns with this balanced fire, yet their influence stretches far beyond their number. Their consistent energy and moderate temperatures create a ring of possibility around them, the habitable zone, where water can flow, chemistry can combine, and biology can take its first uncertain breath. They are the quiet stagehands behind every story of living worlds. Our sun glows at nearly 6,000 degrees on its surface, its light neither harsh nor faint. Deep inside, at 15 million degrees, the true engine hums. There, hydrogen atoms collide and merge, forming helium and releasing torrents of energy. Each second, 600 million tons of hydrogen vanish into light. Yet the balance is exquisite. Gravity pulls inward with relentless force, and fusion pushes outward with equal grace. The result is serenity, a self-correcting harmony that can last for 10 billion years. Every ray of sunlight that touches Earth began in that furnace. A single photon spends tens of thousands of years bouncing from particle to particle before finally reaching the surface and escaping into space. It then travels for 8 minutes across 150 million kilometers to strike a leaf, a wave, or a waiting face. The warmth we feel is ancient, energy born before the first humans, released in silence and carried across time to sustain everything we know. Inside the core, fusion proceeds mostly through the proton-proton chain, but in the hotter depths of some yellow suns, the CNO cycle awakens. Carbon, nitrogen, and oxygen atoms act as catalysts, allowing hydrogen to merge more quickly. This subtle process enriches the stellar interior with trace amounts of heavier elements, laying chemical groundwork for the future. The balance of these reactions determines a star's metallicity, the proportion of heavy atoms within it, and that, in turn, shapes the kinds of planets that can form an orbit. A slightly higher metallicity tends to yield rocky worlds like Earth. Too little, and only gas and ice can take shape. Our sun's composition places it in the cosmic sweet spot. Its golden light contains within it the memory of earlier stars, long-dead giants that forged carbon, oxygen, and silicon in their hearts and scattered them into the nebula that became our solar system. The sun did not arise alone. It was born in a cluster, surrounded by hundreds of siblings now scattered across the spiral arm. Every time we study another yellow sun, we glimpse one of those possible brothers or sisters, still shining far away, each nurturing its own planets, and perhaps its own forms of life. If you could watch the sun up close, you would see a surface alive with motion. Granules the size of continents rise and fall in convective waves. Magnetic fields twist like invisible ropes, shaping arcs of plasma that leap hundreds of thousands of kilometers high before collapsing in graceful spirals. Sunspots darken and brighten in 11-year cycles, the pulse of a living sphere. These cycles govern not just our space weather, but perhaps even the subtle rhythms of climate and life on Earth. Even calm stars have heartbeats. Across the galaxy, other yellow suns beat with their own steady rhythms. Alpha Centauri A, just 4 light-years away, is slightly larger and hotter than ours, a twin in almost every respect. Its light would paint alien landscapes in the same gentle gold. Tau Ceti, in the constellation Cetus, glows a bit dimmer but older, its planetary system crowded with rocky worlds. Farther away, 16 Cygni A and B orbit one another in a slow, stellar waltz, each a yellow sun shining upon its own circle of potential. These stars are beacons of habitability, rare pockets of stability amid a restless cosmos. Around such stars, chemistry has the time to dream. Ultraviolet radiation is mild enough not to destroy molecules, yet strong enough to spark reactions. Oceans can linger, atmospheres can stabilize, continents can drift slowly under skies of gentle light. Life, fragile, improbable life, has a chance to evolve complexity. If intelligence ever gazes upward from another world, its first understanding of the universe will come bathed in the same color of sunlight that warms our own eyes. Yellow suns also act as factories of transformation. As they age, their cores slowly fill with helium. The balance shifts. Fusion continues in surrounding shells, producing new traces of carbon and oxygen. Stellar winds carry this enriched matter outward, seeding interplanetary space with the raw ingredients for future worlds. When we breathe, we draw in oxygen atoms that were once part of a star like ours. When we write, the carbon in our hands was born in stellar fire. In the chemistry of life, we are extensions of these quiet furnaces. The energy of a yellow sun shapes the magnetic fields and atmospheres of its planets. Its winds sculpt auroras, carve comet tails, and fill the emptiness between worlds with charged whispers. Around distant suns, exoplanets bask in similar tides of invisible power. Astronomers now measure their brightness dips, mapping the silhouettes of unseen worlds. Each detection, a shadow against a yellow disk, is a small echo of what our ancestors once saw in the sky and called the dawn. If we could stand on an alien shore beneath such a star, the scene would feel hauntingly familiar. The horizon would glow amber at sunrise, oceans would flash gold at noon, and the long shadows of evening would fall in a tone both strange and comforting. The constellations might differ, but the feeling would be the same: warmth, balance, and continuity. The physics that powers our sun also powers that one, linking every distant morning into a single, continuous light. Over billions of years, yellow suns slowly grow brighter. The sun today shines about 30% more strongly than when Earth first formed. One day, that increase will end our age of comfort. Oceans will evaporate, the sky will haze, and life will retreat into memory. Yet that end is still billions of years away. We exist at the perfect midpoint, the brief golden hour of our star's life, when everything is possible and light feels everlasting. In cosmic terms, this is the moment of grace. When their hydrogen is finally gone, yellow suns begin to transform. The core contracts and heats, and new layers ignite. The star swells into a red giant, its atmosphere drifting outward in vast shells. Inside, new elements form: carbon, oxygen, neon. Eventually, the outer layers peel away into a glowing planetary nebula, a final exhalation. What remains is a white dwarf, a diamond-bright ember the size of Earth, but containing half the sun's mass. It will cool for trillions of years, a quiet monument to the light that once was. And yet nothing is truly lost. The gases expelled by dying yellow suns mingle with those from other stars, forming new clouds, new seeds of creation. In time, gravity gathers them again, and from the ashes of old light, new stars are born. The universe is a recycler of radiance. Every dawn, every breath, every spark of thought is borrowed starlight returning home. The atoms that will one day make another living world may already be drifting outward from our own fading sun. Across the spiral arms of the Milky Way, hundreds of billions of yellow suns burn right now, each keeping vigil over its family of worlds. Their combined glow forms the soft golden haze we see when we look toward the galactic plane. They are the quiet heart of the cosmos, the gentle mediators between the violence of giants and the silence of dwarfs. In their calm fire, the universe learns what endurance can mean. They are the balance point of everything that lives between chaos and stillness. When you feel the warmth of sunlight on your skin, you are feeling a story older than time. A photon that began its journey in a sea of plasma now touches a living world and becomes memory. The sun, and all yellow suns like it, are reminders that even in a universe built on change, there can be constancy. Their glow is both heartbeat and lullaby, the soundless promise that light, given time, can become life. And as long as they shine, the cosmos will never be entirely dark. Some stars are born to burn fast and bright, immense, magnificent, and short-lived. They live like lightning, shaping galaxies in the briefest of instants. These are the blue giants, the titans of light and fury. They shine with the heat of creation itself, their surfaces so hot that they glow in a searing blue-white brilliance. Where a yellow sun might last 10 billion years, a blue giant may live for only a few million. They are the universe's grand gestures, the fireworks that light up cosmic history. Blue giants form in the densest, richest clouds of gas, where gravity gathers matter on an enormous scale. Dozens of solar masses fall inward, compressing to a point where fusion ignites almost immediately. The result is a star hundreds of thousands of times brighter than our sun. Their temperatures reach 30,000 degrees or more, and their radiance floods entire regions of space with ultraviolet light. They are the sculptors of their surroundings, blasting away nearby gas clouds and triggering new generations of stars in the process. Their light is intense, their gravity immense, and their lives spectacularly brief. While our sun fuses hydrogen quietly in its core, a blue giant burns through its supply with furious speed. In just a few million years, the hydrogen is gone, and heavier elements begin to fuse in successive layers. Helium into carbon and oxygen, carbon into neon and magnesium, then neon into silicon. Finally, silicon into iron. Each layer burns hotter and faster, like nested engines stacked within one another, until the fuel is gone and the star faces its inevitable collapse. We can see blue giants scattered across the night sky, the rare jewels of the galaxy. Rigel, in the constellation Orion, glows as a blue-white beacon marking the hunter's foot. It is more than 20 times the mass of the sun and radiates 60,000 times as much light. Deneb, in Cygnus, forms one point of the summer triangle. It is a supergiant nearly 200 times larger than the sun, so bright that if it were as close as Sirius, it would cast shadows at night. Spica, in Virgo, spins so fast that its equator bulges, its shape flattened by its own speed. These stars are visible from Earth, not because they are near, but because they are extraordinarily powerful, blazing torches across vast distances. In their hearts, matter undergoes alchemy on an unimaginable scale. Hydrogen, the simplest atom, fuses into helium, releasing energy. As the hydrogen runs out, the star contracts, heating its core until helium begins to fuse into carbon and oxygen. When that fuel is gone, the process continues, a cascade of reactions building ever heavier elements. Carbon into neon, neon into magnesium, magnesium into silicon, silicon into iron. Each step burns faster than the last. The final fusion of silicon to iron lasts barely a day. And then the music stops. Iron is the great full stop of stellar life. Fusing iron consumes energy rather than releasing it, and once the core fills with iron, the star can no longer resist gravity. The immense outer layers collapse inward in a fraction of a second, crushing the core into a sphere of neutrons or, if massive enough, into a black hole. What follows is a supernova, one of the most powerful explosions in the universe. In that instant, the elements heavier than iron, gold, platinum, uranium, are born. For a few weeks, the dying star outshines its entire galaxy. Then slowly, it fades, leaving behind the ashes from which new worlds will form. The heavy elements that make up our planet, the iron in our blood, the calcium in our bones, the gold in our rings, all began in stars like these. Blue giants are the universe's ultimate forges. Their brief, furious lives end in death, but their deaths give birth to everything solid and beautiful. Without them, there would be no Earth, no life, no memory. Every time we hold something made of metal, we are touching the residue of a supernova, the last breath of a blue giant that once shone like a god. Not all blue giants end in destruction. Some, especially those in binary systems, lose mass to a companion and fade quietly into white dwarfs. Others collapse into neutron stars, dense, spinning remnants that emit beams of radiation as pulsars. A few become black holes, invisible wells of gravity, where even light cannot escape. Their fates differ, but their stories share the same theme: brilliance, transformation, and return. They live fast, die violently, and leave behind the ingredients for creation. In a sense, they are the heartbeat of evolution itself. If you could stand near one of these stars, though no world could truly survive there, you would see a sky filled with raw power. The light would be blue and blinding, casting no shadow sharp enough to rest in. Space would shimmer from radiation, the vacuum itself alive with energy. The star's winds would blow faster than sound, stripping away any atmosphere from nearby worlds. Yet in that chaos, there would also be beauty, a brilliance so pure it borders on silence. Blue giants are the paradox of existence made visible. Violence that creates, endings that give birth. The most massive among them become supergiants, swelling to sizes so vast that if placed at the center of our solar system, their edges would reach beyond Jupiter. Their outer layers are tenuous, glowing with the color of electric fire. Deneb, for example, is nearly 200 times the sun's radius and radiates as much energy in 6 days as the sun will in its entire life. Inside, concentric shells of fusion burn simultaneously, each producing its own light and heat, each preparing for the final moment when gravity will claim it all back. For all their might, blue giants are rare. In the Milky Way, only 1 in a million stars is born massive enough to become one. Yet their influence extends across galaxies. Their light ionizes vast clouds of hydrogen, creating nebulae that shine long after the star itself is gone. Their deaths seed interstellar space, with the building blocks of planets and life. Even their radiation, once thought destructive, may help form complex organic molecules in distant clouds. They are both destroyers and midwives, the universe's paradox incarnate. When we look up at Orion's belt, Alnitak, Alnilam, and Mintaka, we see a trio of such giants aligned across the night sky. Each is thousands of times more luminous than the sun, and each is already nearing the end of its life. Their combined light creates one of the most recognizable constellations on Earth. To ancient civilizations, they represented gods, hunters, or paths to eternity. To astronomers, they are reminders that brilliance comes with brevity. In the time it takes humanity to write its history, a blue giant can live and die, leaving only a nebula to remember it. The story of blue giants is the story of impermanence, of power that cannot last, but must burn anyway. They show us that even in a universe defined by decay, creation and destruction are intertwined. Their light travels for thousands of years, crossing interstellar space, reflecting off dust, finding its way to our eyes. When we see the pale blue of Rigel or the glow of Deneb, we are seeing the echo of life's beginning written in fire. These are the stars that die so that others may live. Their legacy is everything that shines after them. And one day, far in the future, when the last blue giant burns its final fuel and the universe grows quiet, its atoms will still drift among the stars, waiting to begin again. In the end, their brilliance does not vanish. It transforms. From their ashes, new suns will rise, new worlds will form, and new eyes will look to the heavens, seeing the same light reborn. The blue giants remind us that even the briefest life can change eternity, that even 1,000,000 years, if spent burning bright, can leave a glow that never truly fades. Not all stars live in silence. Some pulse with rhythm, their brightness rising and falling like a cosmic heartbeat. Others live in violent surges, swelling with light, and then collapsing into shadow. And some end their lives in explosions so immense they briefly outshine entire galaxies. These are the variable stars and the supernovae, the restless souls of the universe. the moments when the cosmos remembers that creation and destruction are the same song, played at different tempos. A variable star is a star whose light changes with time. Some vary by only a few percent, others by 100-fold. The reasons differ. Sometimes the star expands and contracts. Sometimes spots or companions dim its light. But all variable stars share one thing: motion turned into rhythm, pressure turned into music. They are the beating hearts of galaxies, marking time across the ages. Among the most famous are the Cepheid variables. These are bright, yellow-white giants, whose outer layers pulse in a precise pattern, expanding, cooling, contracting, and heating again in cycles that can last days or weeks. Each pulsation causes the star's brightness to change dramatically, as though it were breathing. Delta Cephei, the prototype of this class, was first observed in the 18th century, and its light has guided astronomers ever since. The longer a Cepheids period, the brighter it is, and that relationship allows us to measure distances to distant galaxies. Cepheids are the universe's lighthouses, blinking steadily across the dark sea of space. Polaris, the North Star, is one such Cepheid. It brightens and fades by a few percent every 4 days. Its change is subtle to the naked eye, but profound in meaning. Each pulse is caused by helium atoms in its atmosphere, trapped between ionization states, alternately absorbing and releasing energy. That rhythmic exchange makes the star literally breathe with light. Even now, as we navigate by its steadiness, Polaris is gently expanding and contracting, a heartbeat woven into the northern sky. Other variable stars live even wilder lives. Mira, in the constellation Cetus, swells to become visible to the naked eye, and then vanishes again over the course of 11 months. It is an aging red giant, its atmosphere drifting away in dusty waves. RR Lyrae stars, smaller and older, flicker rapidly within hours, the remnants of a much earlier generation. Each type of variable star tells a different story, but together they give the universe a rhythm, a breathing pattern written in light and gravity. To understand why stars pulsate, we look to their interiors. When a layer of gas becomes too opaque, it traps heat and expands. As it rises and cools, it becomes transparent again and collapses inward. The process repeats endlessly, like a bell ringing in slow motion. In this way, a star becomes both instrument and musician, playing a song only gravity can hear. The frequencies of those oscillations tell astronomers about the star's internal structure, just as the vibrations of a musical note reveal the shape of the instrument that produced it. But some stars do not simply pulse, they erupt. As massive stars reach the end of their fuel, fusion falters, and gravity begins to win. The core contracts, heats, and then, in one final instant, collapses entirely. The outer layers rebound in a shockwave that tears the star apart. This is a supernova, the most powerful event known in nature apart from black holes. For a brief time, a single dying star can outshine 100 billion suns. The last supernova visible to the naked eye in our galaxy occurred in 1604, observed by Johannes Kepler. In the Large Magellanic Cloud, another erupted in 1987, ESN 1987A, allowing modern astronomers to witness such an event up close for the first time. Its light revealed a sequence of fusion layers laid bare: oxygen, silicon, carbon, iron. For months, the expanding cloud glowed like a ghostly ring. Even now, decades later, telescopes can see the shockwave expanding. lighting up the gas around it, like an echo of the universe's own beginning. In those brief moments of annihilation, the cosmos forges its heaviest elements. When the core collapses, neutrons flood the matter, capturing within fractions of a second and forming atoms far beyond iron, gold, platinum, uranium, and many more. These elements do not form in steady stars. They require catastrophe. The gold in a wedding ring, the iodine in our bodies, the uranium that powers reactors, all were born in the heart of a dying sun. Supernovae are nature's furnaces of finality, transforming death into raw material for new worlds. Some supernovae leave behind a dense remnant, a neutron star. Others, if the original star was massive enough, collapse into black holes. In the case of neutron stars, the outer layers are blown away, but the inner core, no bigger than a city, spins rapidly, emitting beams of radiation as a pulsar. 1 teaspoon of its matter would weigh billions of tons. These remnants, impossibly dense and ancient, drift through the galaxy as the bones of stars, glowing faintly with the memory of their former lives. Betelgeuse, the red supergiant at Orion's shoulder, is one of the next candidates for such an ending. It swells and dims periodically, a variable star nearing its death. When it finally goes supernova, whether next year or 100,000 years from now, its light will rival the full moon in our sky. For weeks, nights will glow softly, and humanity will watch the universe's cycle of death and rebirth unfold before its eyes. Even now, Betelgeuse's fading and brightening reminds us that the clock is ticking. Supernovae are rare, but their impact is eternal. Their shockwaves sweep through interstellar clouds, compressing gas and triggering new generations of stars. Each explosion sends out atoms of carbon, oxygen, calcium, and iron, ingredients that will someday form worlds and creatures. They are not merely endings, but beginnings in disguise. The death of one star can ignite the birth of hundreds more, the universe recycling itself with every flare of light. If you could watch from a safe distance as a supernova bloomed, you would first see a sudden flare, brighter than any other object in the galaxy. Then, slowly, the light would fade into a shimmering nebula, a cloud of glowing gas and dust expanding through the dark. Over centuries, it would stretch across light years, eventually cooling and merging into the interstellar medium. From that debris, new stars would emerge, each carrying traces of the one that came before. The universe breathes through these explosions, a slow exhalation of creation and renewal. Variable stars and supernovae remind us that even the most stable systems must change. Light itself flickers, expands, collapses, and transforms. Without these fluctuations, the universe would stagnate. No new stars, no new elements, no new beginnings. The cosmos survives through motion and change. The same truth holds for us. Nothing lasting ever stays still. In the end, these stars, the breathing Cepheids, the flickering giants, the exploding titans, are all part of one long rhythm. The pulse of gravity and light, the rise and fall of brightness, the heartbeat of time. When we look up and see them shimmer, we are seeing the universe's own pulse, a living tempo written across billions of years. It beats in light instead of sound, but it is as familiar as our own. A reminder that even in silence, the cosmos is always alive, always moving, always dreaming in brightness and in shadow. When a massive star collapses, its death cry doesn't fade into silence. It condenses into something more enduring. What remains is not dust or gas, but a monument to pressure and time, a neutron star. It is the smallest, densest object the universe can make before it tears space itself apart. No fusion burns within it. No light radiates from its surface. Yet it is not dead. It spins. It hums. It pulses. It becomes a timepiece of the cosmos, a relic that marks the boundary between existence and oblivion. To understand what a neutron star is, imagine taking a mountain or an entire continent and crushing it until every atom collapses. Protons and electrons merge into neutrons, leaving behind an ocean of subatomic matter packed tighter than anything we can conceive. The result is a sphere barely 20 kilometers across, smaller than a city, heavier than the sun. A teaspoon of its material would outweigh the Himalayas. It's as if gravity has written poetry in the language of extremes. Inside, the laws of physics bend. The outer crust is a lattice of iron nuclei compressed until they behave like one solid sheet. Beneath that crust lies a strange region where neutrons drip like raindrops, merging into a superfluid that flows without friction. Deeper still, at the core, matter might dissolve into a soup of quarks, the raw ingredients of all particles, or something even stranger that no human equation yet describes. Here, quantum mechanics and relativity meet, and neither wins. The neutron star exists in that paradox, absolute stillness, held together by impossible motion. When the core first collapses, the dying star's rotation increases dramatically. Conservation of angular momentum, the same principle that makes a figure skater spin faster when pulling in their arms, turns a once slow rotation into a blur. The newborn neutron star can spin dozens, even hundreds of times per second. As it shrinks, its magnetic field intensifies to unimaginable strength, 1 trillion times stronger than Earth's. That magnetism accelerates charged particles into beams that shoot from the poles, sweeping through space like searchlights. When those beams cross Earth, we see rhythmic flashes, the heartbeat of a pulsar. Pulsars were first discovered in 1967 by Jocelyn Bell Burnell, then a graduate student who noticed a precise, repeating signal on a radio telescope, a steady beat coming every 1.3 seconds. It was so regular that scientists briefly wondered if it could be artificial, and the signal was humorously labeled LGM1 for little green men. But the universe had simply built a better clock. What Bell had discovered was a spinning corpse of a massive star, its beams sweeping past Earth like the second hand of a cosmic watch. It was the first time humanity had heard a dead star speak. Since then, thousands of pulsars have been found across the Milky Way. Some spin just once per second, others hundreds of times each second. Millisecond pulsars that whirl faster than a kitchen blender. These ancient remnants act as lighthouses for navigation, timing, and even mapping space-time itself. They are so precise that astronomers use them as cosmic clocks, detecting tiny ripples in the fabric of space, gravitational waves, by observing how their beats change ever so slightly over years. The universe's rhythm is written in their silence. The Crab pulsar, lying 6,500 light-years away in the constellation Taurus, is one of the most studied. Born in a supernova, seen by Chinese astronomers in the year 1054, it still spins 30 times every second, emitting bursts of radio, invisible, and X-ray light. The cloud around it, the Crab Nebula, glows because of those pulses, expanding slowly into interstellar space, like the echo of a divine drumbeat. That steady rhythm has lasted nearly 1,000 years. Each flash the after-image of a death that became a new form of life. If you could somehow stand on a neutron star, though no human could survive the attempt, the gravity would be 200 billion times stronger than Earth's. You would weigh more than Mount Everest. A grain of sand dropped from a meter above would strike the surface at 1/3 the speed of light. The crust would be smoother than glass and harder than diamond. Beneath your feet, the neutrons would shift and swirl in superfluid waves. Space and time themselves would bend around you. It is a world where physics becomes art, and art becomes fear. And then there are the magnetars, neutron stars born with magnetic fields so strong they could erase the data on every credit card on Earth from halfway across the galaxy. Their surfaces crack under the stress, releasing bursts of gamma radiation powerful enough to disrupt satellites orbiting Earth. In 2004, one such flare from the magnetar SGR 1806-20 briefly altered Earth's ionosphere, an invisible ripple of energy crossing 50,000 light-years in under half a second. The dying breath of a star touched our sky, and we felt it. But for all their violence, neutron stars are models of order. Their pulses are so consistent that they rival atomic clocks in accuracy. Some drift by less than 1/1,000,000th of a second per year. This regularity makes them perfect tools for mapping the universe. When two pulsars orbit each other, their combined signals reveal the invisible warping of space-time, proving Einstein's predictions once again. The binary pulsar P, SRB, 1913 plus 16, discovered in 1974, showed for the first time that energy is indeed carried away by gravitational waves. Decades later, detectors like LIGO and Virgo would hear those waves directly, confirming what the pulsars had been whispering all along. Sometimes, two neutron stars themselves collide. In 2017, scientists observed one such event, a kilonova, when the light and gravitational waves from a merger reached Earth almost simultaneously. In that collision, elements like gold, platinum, and uranium were forged in vast quantities. The jewelry we wear, the technology we build, even parts of our own bodies owe their existence to those moments of cosmic impact. The universe's rarest treasures are born not from calm, but from catastrophe. Inside neutron stars, matter behaves like nothing else in nature. Neutrons form a quantum liquid capable of rotating in quantized vortices, invisible whirlpools that store angular momentum. When one of these vortices moves or breaks, the star suddenly changes its spin, producing a glitch, a tiny jump in rotation speed that astronomers can detect from Earth. Even dead stars twitch. They are restless in their stillness, reminders that no equilibrium lasts forever, even for the most disciplined clock in the cosmos. Neutron stars also defy our sense of time. Their signals travel for thousands, sometimes millions of years before reaching us. When we hear their pulses today, we are hearing events that happened before humans walked upright. Each flash is a message from the past, still repeating faithfully across the dark. In this way, they become the archivists of the universe, librarians of loss, their light preserving the story of stars long gone. If you could convert their radio signals into sound, you would hear clicks, buzzies, and steady rhythms, each unique to its source. Some sound like slow heartbeats, others like the ticking of a metronome. Millisecond pulsars would produce a note so high-pitched it blurs into a hum. The universe, if translated to audio, would be a symphony of patience. Every pulse a reminder that energy, once created, is never wasted. It only changes form, echoing onward in infinite variations. Neutron stars and pulsars are proof that endings are not always silent. They embody the balance between chaos and precision, between the fury of creation and the discipline of endurance. They show that collapse can give rise to rhythm, that silence can still contain song. Somewhere, far from any living world, a tiny sphere spins endlessly, whispering across the vacuum. Its light may fade, but its timing will not. It will keep pulsing long after our species is gone, long after the galaxies have shifted, counting the seconds of eternity with perfect grace. To know of them is to be reminded that nothing truly disappears. Even the dead can still shine. Even the remnants of destruction can carry beauty. The neutron star, cold, small, and relentless, is the universe's way of saying that permanence exists, if only in rhythm. Every pulse that reaches us is not just a flash of radiation. It is the memory of a sun, the echo of a heartbeat that once lit up the heavens. In their patient ticking, we hear the cosmos itself keeping time, promising that even in darkness, something endures. In the long life of a star, there comes a moment when even gravity wins, when the fire is gone, when all resistance collapses inward, and when light itself can no longer escape. The universe writes its final punctuation mark: a black hole. They are the most mysterious objects in existence, not because they are unknowable, but because they are absolute. In them, the rules of physics fold in on themselves. They are not places in space, but endings of space itself. Where a black hole begins, geometry stops, and gravity becomes a story about time. A black hole is born when a massive star dies so completely that not even a neutron star can survive the collapse. The core's density rises beyond the limits of matter. Even neutrons, those stoic survivors, are crushed into nothingness. The pull of gravity becomes infinite at a single point, the singularity, a region smaller than any measurement can define. Around it lies the event horizon, the boundary where escape becomes impossible. Once something crosses it, light, matter, even time, it can never return. From the outside, a black hole appears perfectly calm, its violence hidden behind a surface of silence. If the neutron star is the heartbeat of the cosmos, then the black hole is its still breath, the moment of perfect stillness after a storm. Yet, paradoxically, it is not dead. It moves, it grows, it interacts, it devours and creates, bends and illuminates. Around a black hole, space-time curves so sharply that even time itself slows. An hour near its edge might equal years far away. To watch someone fall toward a black hole is to see them slow down, dim, and freeze. Not because they've stopped, but because time itself stretches into eternity at the horizon. Inside, no one knows what truly happens. The equations break down, the concepts lose meaning, density becomes infinite, space becomes meaningless, and time perhaps ends. Yet for the falling observer, the experience might be uneventful. They would drift past the event horizon without noticing, crossing into a region from which nothing can escape. They would continue to fall until the singularity ends them, crushed into pure information. In that sense, black holes are not monsters. They are librarians, keeping the information of all that has ever fallen in, encoded in ways we barely understand. Stephen Hawking proposed that black holes are not completely black. Quantum mechanics demands that pairs of virtual particles constantly appear and disappear in empty space. Near the event horizon, one of these particles can fall in while the other escapes, carrying energy away. This faint emission, Hawking radiation, means that black holes slowly evaporate over eons, releasing back into the universe the energy they once consumed. Even these titans, the eternal graveyards of stars, have a lifespan. They fade gently into light. The physics of a black hole is the physics of paradox. Nothing escapes, yet they shine brighter than galaxies. How? Because of their disks, swirling storms of gas and dust that spiral inward, heating to millions of degrees as friction tears atoms apart. That hot plasma emits X-rays and radiation across the spectrum, allowing us to see what should be invisible. These accretion disks can outshine entire constellations, glowing with the last light of doomed matter. It is not the black hole itself we see, but its appetite, blazing against the dark. At the centers of most galaxies, including our own, lie supermassive black holes millions or billions of times the Sun's mass. Ours, Sagittarius A, rests in the Milky Way's heart, cloaked in dust and mystery. Though it is 4 million solar masses, it fits within a space smaller than Mercury's orbit. Its gravity anchors our galaxy, keeping billions of stars in their vast, swirling dance. Farther away, in the galaxy M87, another black hole, 6.5 billion times the mass of the Sun, was the first ever imaged directly. In 2019, the Event Horizon Telescope captured its glowing silhouette, a ring of fire encircling shadow. Humanity saw, for the first time, the edge of infinity. Black holes are not destroyers, they are recyclers. The matter that falls into them doesn't vanish. It transforms. It heats, radiates, decays, and eventually, through Hawking radiation or quantum effects, returns to the universe. What enters a black hole may leave as energy after billions of years, diffused across the cosmos as soft whispers of heat. In that sense, they are not tombs, but engines, taking structure and returning entropy, maintaining the balance of cosmic energy. Even nothingness, it seems, must work to keep time alive. They are also lenses, bending light from distant stars around their edges. When light passes near a black hole, it follows the curve of space, wrapping around the invisible mass. To an observer, it looks like a halo, a ring of distorted starlight encircling a void. Gravitational lensing lets us see behind them, around them, even multiple images of the same star flickering in different places. Space becomes liquid near a black hole, and time becomes circular, folding the cosmos into reflections of itself. If you could fall toward one, your view would change in strange and beautiful ways. Ahead, the black hole would grow, its edge sharp and still. Behind you, the entire universe would compress into a bright, curved band of light, every star and galaxy smeared into a single glowing horizon. As you approached the event horizon, time outside would race forward. The universe would age before your eyes, Stars would burn out, galaxies would drift apart, and the sky would fade into darkness. Then, there would be only the blackness and silence. But from afar, that fall would never complete. To an observer at a distance, the falling traveler would appear frozen at the edge, fading slowly as redshift pulls their light into invisibility. It is as if the universe refuses to let anyone witness the final step. Time, in its compassion or cruelty, stretches that instant into eternity. The person falling does not die in your sight. They simply stop moving, becoming part of the horizon, their story absorbed into the geometry of forever. There are smaller black holes, remnants of stars, and there are the giants, the supermassive ones that shape galaxies. But there may also be primordial black holes, tiny ones formed in the early universe, left over from fluctuations after the Big Bang. Some may have evaporated already. Others may still wander, invisible and ancient, carrying the first memories of existence. If they exist, they are fossils from the dawn of time, proof that the universe has always known how to collapse and begin again. In the heart of each galaxy, in the death of each massive star, and perhaps even in the beginning of time itself, black holes play their quiet part. They teach us that endings are not always destructive. Sometimes they are stabilizing, simplifying, returning. When a star becomes a black hole, it no longer shines, but it still holds. Its gravity becomes an anchor, shaping everything around it. Galaxies rotate in graceful spirals because of them. Without their invisible weight, the cosmos would drift apart into unformed chaos. Even philosophically, black holes feel inevitable. They are not intrusions, but consequences, the ultimate expression of gravity's truth. They remind us that compression, patience, and inevitability are as much a part of creation as expansion and light. In them, the universe seems to whisper that stillness is not death, but depth, that even silence can have structure. We fear them because they erase individuality, yet in that erasure lies unity. All things drawn together into one point, one memory, one eternity. Black holes are, in a way, the universe's meditation. They sit in stillness, surrounded by motion. They consume yet radiate, destroy yet preserve, compress yet define. And as they age and evaporate through Hawking radiation, they give back everything they once took. Slowly, gently, in a release so soft it will take longer than the age of all galaxies combined. Long after stars are gone, long after time itself has slowed to a whisper, the last glow of black holes will fade, leaving the universe in perfect, quiet balance. To contemplate them is to face both terror and peace, the recognition that we are temporary, but the pattern is eternal. The atoms in our bodies will someday pass near one, maybe fall into one, maybe reemerge as light. Nothing truly disappears. It only transforms. In their darkness, black holes hold the ultimate promise of renewal, that even the end of all things is still part of the story. And when the last one finally evaporates, releasing its final photon into the cold, empty universe, there will be no witness, only balance. Space will be smooth again, energy evenly spread, and the long echo of creation will have faded into rest. That quiet will not be an absence, but a conclusion. The universe will have finished its sentence. And perhaps, in that silence, something new will stir. the next beginning, waiting in the dark. All stories must end, even the stories written in light. Every star, no matter how vast or small, eventually reaches the moment when its fuel runs out and its fire fades. The night sky we see is a living archive of those endings. Some happening right now, others long past, their light still on its journey to us. To speak of the fate of stars is to speak of the future of everything, for their lives have shaped every atom, every planet, every living thing. When the stars go out, the universe will exhale for the last time. The small, steady stars, red dwarfs, will be the longest survivors. They burn their hydrogen slowly and gently, consuming their fuel with patience rather than passion. Where massive stars live only millions of years, red dwarfs can endure for trillions. Not one has yet died in the entire history of the universe, for the cosmos is still too young. When the rest of the heavens have dimmed, these faint embers will still glow, keeping their tiny planetary systems warm under red twilight skies. Around them, perhaps, civilizations may rise and fall countless times before the last one flickers out. Eventually, even these patient stars will exhaust their hydrogen. When that happens, they will shrink and fade, becoming blue dwarfs, a phase that has not yet existed, but will in the far future. These stars will cool over trillions more years, their light dimming to invisible infrared, then to nothing. The blue dwarfs will become black dwarfs, cold, quiet spheres of carbon and oxygen, invisible against the eternal dark. The universe will grow still, the last red hues fading into memory. The more massive stars will meet more dramatic ends. Some will collapse into neutron stars, others into black holes, as we have seen. But the white dwarfs, the quiet remains of stars like our sun, will fill the universe for a long, long time. A white dwarf is a stellar ember, a carbon crystal the size of Earth, but as heavy as the sun. Its glow comes not from fusion, but from leftover heat, radiating slowly across billions of years. As time passes, it cools and darkens, becoming a black dwarf, another silent monument to a fire long extinguished. For trillions upon trillions of years, the universe will belong to these remnants: white dwarfs, neutron stars, and black holes. Galaxies will grow faint. Star formation will cease as gas clouds are consumed or blown apart. The great spiral arms of galaxies will unravel, their stars drifting away into the void. The Milky Way and Andromeda will merge into a single giant elliptical galaxy, filled with aging stars and quiet ashes. Then even that will fade, leaving behind a thin mist of stellar ghosts circling the darkness. Far into the future, as galaxies drift farther apart, space itself will continue to expand. The light between them will stretch and fade until it becomes radio waves, then nothing. The cosmic background radiation, the afterglow of the Big Bang, will cool below even the coldest atoms. The universe will grow dark to every eye, silent to every ear. Yet motion will remain, slow and deep, as black holes continue to merge and consume the last matter that drifts too close. The era of black holes will last unimaginably long. They will dominate the cosmos for a time beyond human comprehension, quadrillions of years or more. Each one will slowly evaporate through Hawking radiation, releasing tiny quanta of energy into space. The smaller ones will vanish first, the giants last. when the final supermassive black hole dissolves, the universe will be left with only stray photons and particles, the faintest possible whispers of energy scattered through infinite night. At that stage, the universe enters what physicists call heat death, not fire, but equilibrium. No gradients remain. No more energy can flow. No more work can be done. Everything will have spread evenly across space, and time itself may lose meaning, for there will be no change left to measure it by. The stars will be gone, the galaxies forgotten, but the story they wrote, the atoms and memories they left, will linger forever in the dust between realities. Yet even this ending is not tragic. It is serene, for every atom in your body was once inside a star. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it came from the explosions and collapses of ancient suns. You are a continuation of their work, the consciousness of starlight itself, thinking and feeling before returning to the dark. When the last star fades, the universe will not lose its beauty. It will simply rest, its energy evenly spread like a final quiet breath. There are theories that suggest this might not be the end. Some physicists imagine that in the deep future, quantum fluctuations could give birth to new universes, bubbles of space-time budding from the emptiness. Each might begin with its own Big Bang, its own laws of physics, its own stars and galaxies. If that is true, then death itself is not final. It is simply a transition between notes in an endless cosmic song. Somewhere, somehow, new light may rise from the silence. Even if it does not, there is comfort in knowing that our universe has already done what it was meant to do. It has created complexity, life, and awareness. It has allowed matter to look back at itself and wonder. The stars were not eternal because they did not need to be. Their purpose was fulfilled when they gave birth to minds capable of awe. We are their echoes, their dreams, their final act of creation, the moment when light learned to see itself. Imagine that final night, the universe long grown cold, every star gone. Somewhere in that endless dark, a photon, born from the last evaporating black hole, drifts quietly through infinite emptiness. It has no destination, no purpose, only persistence. It will travel forever, through a universe asleep. That lone photon is the last whisper of everything that ever was. The final light of creation, still moving forward, because motion itself cannot be forgotten. In the end, the fate of the stars is the fate of all things: to shine, to fade, and to change form. Energy never dies, it only transforms. Stars become dust, dust becomes worlds, worlds become life, and life, in turn, returns to starlight. The cycle is eternal. When you look up at the night sky, you are not just seeing history. You are seeing your own origin and your eventual return. The stars are not far away. They are within you, burning quietly, waiting to be remembered. So sleep now, as the stars one by one fade above. Know that nothing truly ends. Every dream you have is another spark in the long story of light. The cosmos may rest, but its music will continue in ways we cannot yet imagine. And perhaps, in some future beyond time, when silence fills all things, the universe will awaken again. Take one deep breath and begin to shine once more.
you.